The birth and death of stars. The universe was born in a huge explosion known as the Big Bang 13.7 billion years ago, and has evolved through the repeated birth and destruction of stars. The iron star Earth was born 4.6 billion years ago, or 9 billion years after the Big Bang. The origin of iron. From the creation of the universe to the evolution of life, iron formed the Earth approximately 4.6 billion years ago. It is a material essential to the advancement of human civilization, as well as a metal essential to the evolution of living organisms and human life. Iron is the final product of nuclear fusion, which began at the birth of the universe, and is said to be the most structurally stable element. Iron accounts for approximately 30% of the Earth's weight, and its recoverable reserves are approximately 232 billion tons, far more than any other metal. In this issue, we explore the birth of iron, the process of iron ore formation, and the role of iron, which is essential to the development and evolution of living things, and delve into the origins of iron, which is the starting point of Nippon Steel's manufacturing. Iron, the ultimate creation born from the universe. The origin of iron dates back to the birth of the universe, which is thought to have been created in a massive explosion known as the Big Bang, 13.7 billion years ago. The Big Bang created protons and neutrons, which make up atoms, from a state of nothingness, and they combine to form a helium nucleus, 2 protons, 2 neutrons. At that time, the world was chaotic, with protons, helium, electrons, electromagnetic waves, and other things flying around. It is said that all of this happened in just 3 minutes after the Big Bang, after about 380,000 years, when the temperature of the universe dropped to about 3,000 degrees Celsius. Electrons were attracted to atomic nuclei, forming hydrogen and helium atoms. As the movement of electrons became restricted, the universe cleared up and became clearer. These two energetically stable elements drifted through space for a while, and then, attracted by fluctuations in a substance known as dark matter, they gradually gathered together into gaseous clouds, forming stars. Figure 1. This gravitational force then pressed the atoms together, generating energy through a rise in temperature, which in turn led to the further bonding of protons and neutrons, producing elements other than hydrogen and helium one after another. This is a phenomenon known as nuclear fusion, thermonuclear reaction, figure 2. Each time a reaction occurs, heat is generated, and that heat and pressure cause the reaction to progress further, eventually ending in the formation of iron. When nuclear fusion occurs, the total weight of the atoms increases as the number of protons and neutrons increases. The thermal energy released by the fusion gradually reduces the weight of each proton and neutron. Note, the total mass after fusion is lighter than the total mass before fusion, and the difference in mass is released as energy. See figure 3 = Einstein's special theory of relativity. The protons and neutrons that make up the nucleus of iron are the lightest of all elements. This suggests that nuclear fusion occurring in stars ended with iron, the end of the first generation, figure 3. Of all the various atoms, iron has the lightest proton and neutron mass and the strongest bonding force. When atoms with atomic numbers smaller than iron fuse, they release energy and become more stable iron, while atoms with atomic numbers larger than iron release energy and undergo nuclear fission. Whether there are more or fewer protons than iron, the bonding force weakens. Iron is the most stable of all elements. It can truly be called an iron scrum. Iron is the ultimate creation of the alchemist called the universe. The birth of the iron planet Earth iron is born at the end of nuclear fusion. However, in reality, in a star the size of the Sun, even if nuclear fusion progresses, only elements up to carbon, 6 protons, 6 neutrons, and oxygen, 8 protons, 8 neutrons are produced. Iron is only produced in stars that are about 8 to 30 times the size of the Sun. In the cores of these stars, after about 30 million years, which is relatively fast in cosmic terms, compact iron is produced and nuclear fusion ends, preventing further reactions. However, once nuclear fusion has progressed to iron, the changes do not stop there. Further atoms are attracted from the outside, and the iron nuclei that had previously been stable in the star's core begin to decay. As the temperature and pressure increase further, the protons collide with electrons and turn into neutrons, emitting neutrinos. Some of the large number of neutrinos emitted collide with atoms outside, causing a huge explosion. This is called a supernova explosion. As a result of this gigantic supernova explosion, the products of nuclear fusion, including iron, turn into stardust and are scattered into space, drifting away. Another nuclear reaction occurs in a supernova explosion. All elements visible to us today, from iron onwards in atomic number order from nickel to uranium, were born in this supernova explosion, second generation. The protons and neutrons of these atoms, born from the energy of the explosion, are heavier than those of iron. Figure 3. These second-generation elements are also blown away by the energy of the explosion and drift into space. This is how various elements were born. Due to their origins, the most abundant elements in the universe are hydrogen and helium, the basic elements created in the Big Bang. However, if left alone, the first-generation elements will undergo nuclear fusion and ultimately converge to iron, which is why iron is particularly abundant in the universe. Figure 4. Furthermore, second-generation elements are only produced in supernova explosions, so they are in low abundance, and are tending to converge to iron through nuclear fission and nuclear reactions within stars. When the new sun was born from the accumulation of hydrogen, helium, and other elements floating in space, the temperature at its core rose, causing the hydrogen to burn, and then begin a nuclear fusion reaction to reform into helium, shining brightly. Dust that was not absorbed by the sun gathered in a disk-like shape on the sun's equator, and many planets were born from this accumulation. One of these was the Earth. The Earth, which was born approximately 4.6 billion years ago, was formed by the aggregation of relatively heavy elements due to its proximity to the sun, with iron being the predominant component. Shortly after its birth, the Earth was at high temperatures and partially molten. This allowed for easy movement of matter, and gravity led to the formation of a structure consisting of 3 layers: the core, mantle, and crust. Figure 5. The Earth is made up of oxides of iron, silicon, and magnesium, with iron being the most abundant, accounting for 34.6% of the total weight. Thus, the Earth is a mass of iron. Why is heavy iron on the surface of the Earth? When the Earth was first formed, the atmosphere lacked oxygen and was filled with carbon dioxide, hydrochloric acid, sulfur dioxide gas, and nitrogen. Acid rain fell on the land, dissolving iron from the surface and entering the ocean. At the time, there was no oxygen in the ocean either, so anaerobic oxygen-hating bacteria and other organisms were born in the sea. But about 2.7 billion years ago, cyanobacteria, bacteria similar to algae, were born and began to release oxygen into the sea through photosynthesis. The oxygen combined with iron, forming solid iron oxide, which precipitated and accumulated to form iron deposits. Approximately 1.5 billion years ago, these iron deposits emerged on land due to the uplift of the seafloor, creating what are known as iron ore mines. Figure 5. Iron ore that can be mined open-cut today is layered, evidence that it was once submerged on the ocean floor. Photo 1. Sedimentary iron deposits in ancient strata, widely distributed in North and South America, India, Australia, and Africa, were formed at that time. Currently, the recoverable reserves of iron are 232 billion tons, an order of magnitude greater than those of other metals. Figure 6. However, the iron we use is only that found on the Earth's surface, which is only a tiny fraction of the total amount that exists on Earth. There is also an inexhaustible supply of iron ore on the ocean floor. Furthermore, because iron is heavy, it sank during the formation of the Earth, and the amount increases the closer you get to the core. However, even on the Earth's surface, iron is the third most abundant element after oxygen, silicon, and aluminum. So why is heavy iron on the Earth's surface? The answer is that iron has an affinity that allows it to coexist with many other elements, and it bonds with silicon and sulfur to form light compounds that float up to the Earth's surface in large quantities. Figure 7. Iron ore is formed when iron mixed with sand, which contains silicon, on the Earth's surface flows into the ocean, where it is subsequently oxidized and condensed. Steel creates the energy that gives life. Iron, which is between the first and second generation elements, is roughly in the middle in terms of ionization tendency and binding energy with oxygen. This makes it easier to reduce than titanium or aluminum and requires less energy to manufacture. It also bonds easily with elements of both generations, making it easy to alloy. Furthermore, iron easily bonds with organic matter, which contributed to the evolution of life. Proteins, the origin of life, are thought to have been created by the further combination of amino acids, which were formed by the combination of carbon and hydrogen that erupted from thermal deposits on the sea floor. Metal elements played an important role as catalysts in this synthesis. These proteins then combined to form DNA, which then led to the proliferation and evolution of living organisms. As mentioned earlier, when the Earth was first formed, there was no oxygen, and anaerobic organisms first appeared, page 11. However, after oxygen was produced by cyanobacteria, organisms that absorbed oxygen as energy to fuel their activities appeared, figure 8. Iron played a key role in this process. Iron binds with oxygen and moves throughout the body, carrying oxygen throughout the body, and generating energy. A typical example of this iron protein is hemoglobin in the blood, which is also a symbol of mammals that breathe oxygen. By utilizing iron and oxygen as an energy source, living organisms gained access to a vast energy source. In humans, an adult male weighing 70 kilograms contains approximately 4 to 5 g of iron, the equivalent of one nail, of which approximately 65% is present in hemoglobin. Within living organisms, iron exists in two ionic states, ferrous iron and ferric iron. These can be easily converted by the exchange of electrons, making them useful for a variety of biochemical reactions. Furthermore, the transfer of electrons via iron ions initiates oxidation reactions that slowly burn nutrients such as carbohydrates with oxygen, generating energy for biological activity. Iron is a substance that is highly compatible with the bodies of living organisms and has been incorporated into them as the range of their activities has expanded. Iron also evolves living organisms. Trace amounts of metal elements are essential for humans. These metals bind to specific amino acids and proteins, and act as catalysts for various biochemical reactions. One such reaction is an enzyme called SOD, superoxide dismutase, which is formed by binding proteins with copper, zinc, manganese, etc. Oxygen, essential for living organisms, generates a lot of energy, but too much can damage cellular tissue. The toxicity of reactive oxygen is well known. Reactive oxygen is first broken down into hydrogen peroxide, H2O2, by SOD, and then broken down into water and oxygen by an enzyme called catalase, which is made of iron and protein. Iron combines with protein to form enzymes that have 10 billion times the ability to process hydrogen peroxide as iron alone. The more of these enzymes an organism has, the longer its lifespan will be, figure 9. Throughout the evolution of living organisms, iron has played two major, seemingly contradictory roles. It effectively utilizes oxygen in the body as energy, while at the same time neutralizing excess reactive oxygen species. Since the dawn of history, humans first discovered gold, which does not oxidize and is easy to find in its pure form, and then used copper and iron in that order for tools. However, living organisms have evolved in the opposite direction. They have taken in iron, copper, and manganese in that order, acquiring new functions, figure 8. Iron is an essential material for human civilization, and is also a metal that is essential for the evolution and survival of living organisms on Earth. T. Forget to like and subscribe to follow the next articles of the History and Technology channel. Please share the channel with those who need to know about it. Thank you. Reference: Earth Structure Diagram.